Welcome back. In this video, we'll be looking at section 3.2.6. We'll be looking at integrals of basic trigonometric functions. And now that we have substitution, we'll be able to compute the integral of every single trig ratio, all 6 of them. This is going to be done in proposition 3.2.2. Here are the integrals of the 6 basic trigonometric function. Just an S missing here. All right, so first of all, the integral of sine, that's going to be, I need a function whose derivative is sine, that's minus cos of x. And then if I have just cos, that's sine of x. All right, so these two we knew before, but let's put them there anyways. Then if I look at the integral of tan of x, I get minus log of cosine of x. And if you look at books, sometimes they write it as, you could also say it's ln of secant of x plus c. That's fine too, whichever one you like the best. They're actually the same function. Now if I have the integral of cotan, I'm going to get log of sine of x plus c. Secant, log of secant x plus tan x plus c. And cosecant would be minus log of cosecant x plus cotan x plus c. Don't know if you noticed, but I've placed them in this order because here you have tan, here you have cotan, and the integrals are very similar. And same thing here, sine, cosine, integrals are similar. Every time, the only difference is you put an extra minus, and then every function is replaced by co of it. So if I had cosine, I'd have sine. If I had secant, I'd have cosecant. That's how I remember it. So you really need to remember these three. All right, so let's prove a couple of them. The third one I want to prove is tan, the integral of tan of x. To evaluate it, I'm going to write tan as sine over cosine. Then I'm going to take a substitution. I have cosine in the denominator. Its derivative is on top. So the two hints are pushing me to choose u equals cosine, and then I'll get minus sine as du. So this is going to give me minus 1 du over u, which is minus log of u plus c minus log of cos plus c. Alright, so it's not a hard one. The only thing that's hard is to remember to write it that way so you can apply this substitution. Now 5 is a bit more strange, a bit harder to see where it comes from. It's not actually hard to prove it works. So I'll do a substitution. You could also just differentiate this and check that you get secant. In fact, we've done it almost for this function. I think we got minus cosecant. We did it in section 3.1.1. All right, so let's look at the integral of secant. All right, I'm going to start by doing something very strange and a bit insane. I'm going to multiply this by secant of x plus tan of x over secant of x plus tan of x. So I'm not changing my function, I'm just multiplying and dividing by the same thing. But now if I distribute this, what I'll get is secant squared plus secant x tan x over secant x plus tan x dx. All right, now I'm going to take my denominator. The derivative of secant x is secant x tan x. Derivative of tan x is secant squared of x. Now notice what I have on top is exactly what I have here. So the entire numerator is just du, and then the denominator is u. And so I get ln of u plus c, so ln of absolute value of secant x plus tan x plus c. All right, let me say there's no way any of us would have come up with this idea here. I'm not sure who did, and I'm not sure this is how they first discovered it. It's a bit strange, but now that we know it, we just use the result. This is the integral of secant.